Welcome everybody. Today we talk about magnetic effects of electric current. Recap for science class 10. Magnetic effects of electric current. What are the magnetic effects of electricity is what we will look in this video. We talk about magnetic field, magnetic lines, field due to current carrying conductor, field due to current carrying coil or solenoid, force on the current carrying conductor. We also look at Fleming's left hand rule, right hand rule, electric motor, electromagnetic induction and induced current. What is a magnet? Magnet is a material that exhibits characteristics of magnetism. Magnet is a material that has magnetic characteristics. That means what? It will align itself in an external magnetic field. That means the component atoms in that material is so ordered to act like a magnet. That is a magnet. So magnetism is a capability to attract certain elements by certain other elements. They align itself in the north-south direction. Magnetic material align itself in the north-south direction. The attraction is maximum at the poles. Similar poles do not attract, they repel. Opposite poles attract. They attract materials like iron, nickel, cobalt, etc. Magnetism is because of the characteristics of the atoms present in that metal. What are magnetic field lines? Field or area around a magnet where its magnetic influence can be felt or experienced is called magnetic field lines. The area around a magnetic material where the influence of the magnet can be felt. They are represented as a curved imaginary lines. They do not intersect. They are closed and continuous curves directed from north pole to south pole on the outside. North pole to south pole on the outside. This is the north pole, this is the south pole, this is north pole to south pole on the outside. And inside it is from south pole to north pole. On the inside it is from south pole to north pole. This is south pole to north pole. Inside it is south pole to north pole. On the outside it is north pole to south pole. Closed and continuous lines. They are closer together at the poles. They are closer together at the poles and far apart at the center. Closer together at poles and far apart at the center. The tangent on these lines will give the magnetic field at that part. Tangent when drawn to this imaginary curved line will give the magnetic field. The field cannot have two directions at one point. It can either be directed from north to south or directed south to north. At any given point, it cannot have two directions. These are the magnetic fields. What is a straight line conducting wire? What is a straight line? Now, when current is passed like this on a straight line, magnetic fields like this are caused. Magnetic fields are caused. When current is going like this on a conductor, magnetic fields like this are caused. Now, magnetic field is a form of concentric magnetic lines of a force. Concentric magnetic lines of force. The center lies on the conductor. The center of that force is on the conductor. The strength B is directly proportional to the current passing through. The current passing through will decide how strong is that magnetic force. More the current, more the force. Strength B is inversely proportional to the distance of that point from the wire. If the wire is here, the strength is high. It is inversely proportional to the distance from that point. Inversely proportional to the distance of that point from the wire. 1 by. This inversely proportional is 1 by. If you multiply, it is proportional. If it is 1 by, it is inversely proportional. CGS unit. CGS unit is Gauss. CGS unit is Gauss and SI unit is Tesla. Tesla is the measure of the magnetic force. Tesla T in Newton. Newton per ampere meter. What is a Tesla? Tesla is Newton per ampere meter. How do we write? Newton is N, meter is M minus, ampere is A minus, Newton per ampere meter. 10 power 4 Gauss is 1 Tesla. 10 power 4 Gauss is 1 Tesla. What is Gauss? Gauss is the CGS unit of measuring the force. Newton ampere meter. Now, what is the right hand thumb rule? We have seen when the current passes like this, the magnetic force is like this. When current passes from above to below, the magnetic force is like this. It is opposite. When current passes from above to below, the magnetic current is sort of clockwise. When current passes from below to above, the magnetic current is sort of anti-clockwise, right? So this is explained by this Maxwell's right hand thumb rule. When you have a right hand thumb rule, when the current is coming down, the magnetic field will be in the direction of the curled fingers. The right and the straight thumb points to the direction of the electric current, and the curl of the finger point to the direction of the magnetic field. This is the right hand thumb rule. Now, in case of circular coil, what happens? Suppose you have a circular coil. Magnetic fields are nearly circular and concentric. Magnetic field lines are nearly circular and concentric. Here we have a concentric magnetic lines. Here it is nearly circular and concentric. What are field lines? In the same direction in the space enclosed by the coil. In the same direction in the space enclosed by the coil, it is in the same direction. It is all going like this. You see? The space enclosed by a coil, it is in the same direction. Nearly straight and parallel at the center. At the center, it is nearly straight and parallel. It is not concentric circle. The direction, magnetic field at the center is perpendicular to the plane of the coil. If the coil is like this, perpendicular to the plane of the coil. Perpendicular means what? 90 degrees, right angle as the plane of the coil, and the direction is maximum at the center. The direction is maximum at the center. What is the strength? Strength is increased by increasing the number of turns of the wire. If it is only one wire, it is less strength. If you have more wires, it is more strength. Strength is increased by increasing number of turns. Increased by increasing the current flowing the wire. The more the current flows, the more will be the magnetic field. Third, it is decrease the radius of the coil. Closer the radius of the coil, more will be the strength of the magnetic field caused by the electric field. Magnetic field, this is a positive from the battery. Current flows from here to here. When current flows like this, in this direction, we can assume it is clockwise. The magnetic fields are anti-clockwise. Magnetic fields are anti-clockwise. This is a circular loop or coil carrying the wire, carrying the current. Magnetic field lines are clockwise here. Here it is anti-clockwise, here it is clockwise. Here it is anti-clockwise, opposite of the clock, it is clockwise. Within the coil, it is in the same direction. The same direction, the space enclosed by the coil. This is a coil. Now let us look at a solenoid. What is a solenoid? What is a solenoid? Solenoid is an insulated copper wire wound in a cylindrical shape. Insulated copper wire. This is only a coil. This is a copper wire wound in a cylindrical shape whose length is greater than the diameter. Diameter of the circle is x, means the length of the wire should be more than x. That means what? The length of the carrying conductor should be more higher than the diameter of the cylinder on whom imaginary cylinder on whom the copper wire is insulated or wound around. The magnetic field lines are almost uniform inside the solenoid and directed from south pole to north pole. Directed from south pole to north pole. Non-uniform outside the solenoid. It is non-uniform outside the solenoid and directed from north to south pole. Here it is like this, and here it is like this. Strength is increased by increasing the number of turns. Strength is increased by increasing the strength of the current, and strength is increased by using soft iron rod as a core inside on which this coil is wound on. This is a solenoid. Now what is Fleming's left hand rule? When you throw up your left hand, the thrust or motion caused will be on the direction of the thumb. The magnetic field will be in the direction of the index finger, and the curly finger will be the direction of the current. Straight stretched out index finger points to the direction of the magnetic field. Direction of the curled finger directs the electric current, and the thrust or motion is on the direction of the thumb. Current carrying wire. Current carrying wire creates a magnetic field. How? The experiences of a magnetic force in a magnetic field is felt when a current is carried by a coil, or electricity creates a magnetic field. Now current is flowing like this. The direction of the force will be on the top when this is a north pole and south pole of a magnet. A magnetic field will be in this direction because current is flowing like this. It will be perpendicular magnetic field. Direction of the current and direction of the magnetic field will be opposite. That is what we saw. The index finger and the thumb finger. Direction of the force and direction of the magnetic field and direction of the current will be different, and at right angles. So current carrying wire experiences a magnetic force in a magnetic field when there is a magnetic field, and when there is a current, the magnetic field will give a magnetic force on the current carrying field. This will cause a magnetic field. Now length of the conductor, the current in the conductor will all decide on how much is the force. The strength of the magnetic field, the length of the conductor, the current flowing in the conductor, angle between the element of the length of the magnetic field. This will create the force. So what's the formula for the force? Force is also magnetic field into the current L into the length of the conductor into the length of the conductor and then multiplied by the angle between element and field. Angle between element and field, that angle is theta, sin theta. So F equals to BLR sin theta. F equals to BLR sin theta. Now, what is the principle of electric motor? You have seen an electric motor. Electric motor has coils of copper wire like this, multiple coils, and then you have a shaft, and this shaft turns. The shaft turns when electricity is passed through. So, there is a magnet inside. When there is an electric force as well as magnetic force, when there is a current carrying conductor, the magnetic force will act on the current carrying conductor and it will cause a force. That force will help to turn this shaft. So, the different parts are, there is an iron core, there is a brush, there is a starter magnet, there is an axle which turns the terminals. And then this is the north pole and south pole of the magnet. This is the static magnets. This is a commutator, this is a coil. So you have a magnet, you have a coil, and then what happens is when current is passing through, there will be a force. Current carrying conductor placed perpendicular to the magnetic field experiences a force. The current carrying conductor, this is the current carrying conductor coil, it is placed perpendicular to the magnetic field. This is a north-south pole of the magnetic field. Then it will convert the electrical energy into mechanical energy. Electric motor will convert electrical energy to mechanical energy or mechanical to electrical energy. In either way it can convert. Where it is converting mechanical to electrical? In a dynamo, in a hydroelectric power turbine. The mechanical energy is rotor is turning because of the water that falls on. In a dynamo, the wheel of the vehicle will turn the dynamo. In a motor, in a fan or a mill, electric energy is converted into mechanical energy. It will turn the shaft which will turn something else. So the current carrying conductor placed perpendicular to a magnetic field will experience a force. Now what is electromagnetic induction? Electromagnetic induction is induction caused by electricity and magnetism. The electric current generated by varying the magnetic field. When magnetic field keeps on changing and when there is a conductor in between, what happens is the changes in the magnetic field will cause an induction, will induce electricity. Changes in electricity will induce magnetism, changes in magnetic field will induce electricity. Magnet is pushed into the fixed coil, current is produced in the coil. When magnet is pushed inside the fixed coil where the electric current is to be generated, the varying magnetic field will produce the current in the coil. Varying magnetic field will produce current in the coil. Dynamo works on this principle. Faraday's law says induced current flows through a coil only for a period where there is a charge, there is a magnetic flux. Induced current flows through the coil only for the period during which there is a magnetic flux, there is a charge, there is a change in the extent of magnetism, magnetic field, change in the magnetic flux, which is linked to the coil. So when the magnetism, when the changes in magnetic field happens, electricity is generated. When changes in electric field happens, magnetism is generated. This is electromagnetic induction. What is the right hand rule? The right hand rule is that the stretched out index finger points the direction of the magnetic field. The direction of the curved finger will give the direction of the electric current, while the direction of the thumb will be the direction of the force generated. Movement of the conductor is in the direction of the upward thumb. Movement of the conductor is in the direction of the upward thumb. Forward index finger gives the direction of the magnetic field. Current induced is in the direction of the curled fingers. Motion is in the direction of curled fingers. Motion is in the direction of the curled fingers. What is charge? Electric current is equivalent to the charges or electrons in a motion. Neutron is uncharged particle, proton is a charged particle, electron is a negatively charged particle. So neutron will have no effect because of the magnetism, or electricity and magnetism induction will have no impact on the neutron. Electron is the electric current. When electrons get charged, they get into motion and they cause the current. So if this is a circuit, this is a positive current, current flows from here, this is the conventional flow of the current. The electrons in the conductor will move in opposite direction. Not from electrons in the conductor will move in opposite direction. When current is flowing through a wire, the electrons move inside in the definite direction. When no current is flowing through the wire, the electrons inside the wire are in random motion. They do not move but in random motion. But when current is flowing, the electrons move in a definite direction. So the average thermal velocity is 0. Average thermal velocity is 0. Such a wire does not produce electric field. If the thermal velocity is 0, then such a wire does not produce any electric field. Thanks for watching this video on magnetic effects of electric current.